Hello everyone, a warm greetings to all. I am Dr. Dhrubajit Sarma, Assistant Professor in the Department of Mechanical Engineering, Madanapalle Institute of Technology Science. I'll be giving the first lecture on the lecture series on nanofluid in machining process, recent advancement and contemporary challenges. In this first lecture, I'll be delivering the following topics like thermal aspect of machining, importance of cutting fluid, then problems with the various cutting fluid, then what are the different alternative cooling strategy we should have, then further going into nanotechnology in machining, then what is the different if you use of nanofluid in mql processes, then nanofluid production, that is probably confined using the next slide. So manufacturing is one of the value addition processes by which raw materials of low utility and value due to the inadequate material properties at poor or irregular size, shape, and finish are converted into high utility and valued products with definite dimension, forms, finish, and imparting some functional utility. Manufacturing has been cornerstone of human development and civilization, tracing its root back to the ancient times, when early humans began crafting tools and weapons from stone, wood, and various metals. The history of manufacturing is a story of human ingenuity, resourcefulness, and the continuous quest to improve the efficiency and quality of life. Initially, the manufacturing was localized manual process, often carried out by individual of artisan and craftsmen. This period, known as the pre-industrial era, saw the creation of essential goods through labor-intensive methods that were often passed down through generation. As societies grew and human developed their technologies, that trade networks expanded, the demand for goods increases, in necessitating the evolution of manufacturing processes. The Industrial Revolution, beginning in the late 18th century, marked a pivotal shift in the manufacturing. The advent of mechanization and the development of machinery powered by steam engine revolutionized the production. Then factories slowly began to emerge, centralizing production and significantly increasing the output. This period also saw the introduction of interchangeable parts, which standardized production and simplified assembly and repair processes. Now, this shift from artisanal to industrial manufacturing has not only enhanced the productivity, but also made some good and more affordable and accessible products, thereby driving economic growth and improving the living standard. Next, the 20th century that witnessed further advancement with the introduction to assembly line by Henry Ford, which drastically reduced the time and cost of manufacturing complex product like automobile. Also, this time or this era saw significant technological advancement, including the development of electricity, the internal combustion engine, the advancement of metallurgy, and the advancement of chemical process or various manufacturing processes. Now, this innovation further streamlined manufacturing process and expanded the range of product that could be mass produced. The rise of electronics and computing in the latter half of the century that introduced automation and robotics, which lead to even greater efficiency and optimization and precision in manufacturing processes. Now, today, the manufacturing process is a highly sophisticated and globalized industry. Modern manufacturing process employs advanced technologies such as AI, artificial intelligence, machine learning, and the Internet of Things (IoT) to optimize the production process and improve the quality control and enhance supply chain management. Additive manufacturing, also known as 3D printing, has emerged as a revolutionary technology, allowing for further creation of the complex and customized products with minimal waste. Furthermore, the integration of sustainable practice and green technologies is becoming increasingly important, addressing the need of the environmentally responsible manufacturing processes. The need for manufacturing originate from the fundamental role in the creation of good. the and products that sustain our daily life and drive the economic development. Manufacturing has a diverse application like aerospace, construction, daily utilities, biomedical, etc. Without manufacturing, the development and the distribution of vital products like medicine, vehicle, electronics, clothing, or various sector that will be severely constrained, which will impact our daily aspect of the modern life. Also, manufacturing plays a crucial role in employment, economic development, economic stability. The manufacturing sector provides millions of jobs worldwide, from skilled labor and engineering position to research and development roles. This job support families and communities, fostering economic growth and stability. Also, additionally, the manufacturing drives innovation as companies continuously seek to improve their process, continuously seek to improve their product to reduce cost, reduce the economics in machining, and develop new product. This innovation is critical for maintaining competitive advantage in the global market and also to contribute in the overall advancement in the technology and the industry. So, to if we put in a nutshell, manufacturing has continuously evolved from early tool making to the complex and automated process of today to meet the growing and ever-changing need of the society. It is very essential for the product to produce goods and product that sustain life, which will drive economic growth and foster innovation. The sector provides employment, it supports economic stability and ensures the national security, making it one of the indispensable part of the modern world. In summary, the manufacturing leads to economic growth of the society, innovational technological advancement, infrastructure and development, quality of life improvement, and environmental stability. Now, coming to the various approaches of manufacturing, generally we have two types of manufacturing approach. One is top down, which is also known as subtractive manufacturing. One, the next one is known as bottoms up, that is known as additive manufacturing. Com- uh, in these two methods, subtractive manufacturing is from the history, starting history of the manufacturing process. It has been followed, but in the 20th century, after the advancement of various technology, the additive manufacturing has come as a new and advanced process which will reduce the cost, which will reduce the time, and which will improve the product quality. We'll go one by one. First, coming to the subtractive manufacturing, it is a process where metal is removed from the solid block or workpiece to create a desired shape or product. From the figure, we can see that we are having a solid metal block. From that, various machining process, different machining process has been done to create a final product. Also, it will have some waste material. Uh, Contrast to additive manufacturing, where metal is often added layer by layer, the additive subtractive manufacturing include milling, turning, drilling, or nowadays it utilizes various modern tools like CNC, which is a computer numerical control for precision and efficiency. It's widely used in the industry, requiring high accuracy and quality finish, like aerospace, automotive, medical device, biomedical device, instrumentation, etc. The process allows for production of complex geometry and detailed texture, although it often results in material waste like this. Now, coming to the second and advanced method known as additive manufacturing. This is the figure for additive manufacturing. Additive manufacturing, it is also commonly known as 3D printing. It is a transformative approach of the industrial production that enables the creation of lighter but stronger pattern system. In this system or in this process, objects are built layer by layer from digital model. The digital models are first generated in the computer digitally by various R&D team. Then it is converted into the final product through the AM machines. The additive manufacturing offers unparalleled design flexibility and efficiency. This technology reduces material waste, it reduces the production time, and allows for complex geometry that are very difficult or impossible to achieve through the traditional manufacturing method. Nowadays, the additive manufacturing has been widely used by the industries such as aerospace, healthcare, automotive, etc. The aim additive manufacturing is revolutioning the production process, enabling customized on-demand manufacturing and increasing the innovation across various sectors. Now, coming to the classification of manufacturing process. In this classification, we will focus in totally into the subtractive manufacturing part. We will not cover the additive manufacturing part here. So the subtractive manufacturing has different sub division like machining, forming, joining, casting, powder metallurgy, sheet metal processing, finishing, etc. So we'll cover one by one. First, machining. Machining is a manufacturing process that involves the removing of material from a workpiece to shape it into a desired form. This is typically done using tools like lathe, milling machine, drills, etc. Machining processes are essential for creating precise component with fine detail and tolerance. Second is the forming. So forming process used to manipulate the shape of material without adding or removing the material. This category often includes techniques like forging, rolling, extrusion, and drawing. Forming is often used for metals and involve plastic deformation to achieve the desired property or desired geometry. So next is the joining process. Joining process often involved connecting two or more components to create a single assembly. Common joining techniques include welding, brazing, soldering, and adhesive bonding. These processes are very crucial into assembling parts of various materials and sizes in industry like automotive and aerospace. Next is the casting. Casting is a sub part of the manufacturing process that where molten metal is poured into a mold and allowed to solidify for a specific time to achieve a desired shape and size. This method is widely used for creating complex shape and large component such as engine block with the material like metal, plastic, and ceramic, etc. Now, going to the next part, powder metallurgy, it involves producing components from powdered material through compaction and sintering. This process is ideal for manufacturing part with unique material property and precise dimension, which is commonly used in industries requiring high performance material like aerospace and automotive. Next is the sheet metal processing. Sheet metal processing encompasses various techniques to cut, bend, and shape metal sheet into desired form. This method include shearing, stamping, bending, and deep drawing. This process is prevalent, such as in industries such as automotive, construction, appliances, where metal sheets are the primary material. Now, coming to the importance of machining in the manufacturing industry process or manufacturing industry, we'll go to the first topic, machining. The machining is already we have conveyed that machining is a process to remove the excess material in the form of chip or otherwise to give the desired shape, size, desired surface roughness, tolerance on the workpiece obtained from a primary manufacturing process. Uh, through manufacturing or so through machining, a wide range of material can be manufactured with very close tolerance level. We can have a variety of materials for machining. Variety of shape and special geometry can be included. In summary, in machining, we are using a single point cutting tool or a multi-point cutting tool to remove the material by shear deformation. Now, one of the major aspect in machining is the thermal aspect. So, in machining process, the thermal aspect plays a very crucial role in determining the quality and efficiency of the operation. Now, heat generation occurs primarily due to the plastic deformation of the workpiece material and the friction between the cutting tool and the workpiece. This heat can adversely affect the tool life, causing the thermal distortion in the workpiece and alter the material properties also, which potentially leads to the surface defect and dimensional inaccuracy. But uh, through heat effective heat management, through proper cutting parameters, use of various cutting fluid or advanced cooling technique to mitigate this thermal effect, which will ensure the precision, which will enhance the tool life, and it will maintain the structural integrity of the machine component. Now, in the machining zone, there is various heat generation, very enormous heat generation in the workpiece and tool contact surface. The heat generation in the tool and workpiece contact zone, it may be classified into two parts. First, heat generation due to the shearing. Uh, in this one, the shearing in the shearing zone, what happens? The heat is generated due to the plastic deformation of the workpiece. The this is happened due to the mechanical energy conversion into thermal energy. Second one is the heat generation due to the frictional heating. In heat, this one, frictional heating takes place in the form of chip tool interface region. The rate of energy input in the friction is the product of frictional force and the sliding velocity. Now, in the machining process, we are having different deformation zone. In the figure, this is the workpiece, this is the tool, and the materials are being removed on the form of the chip. So we are having one deformation zone that is known as the primary deformation zone here. We are having the secondary deformation zone in this one, and the third one we are having the tertiary deformation zone in between the tool and the workpiece endpoint. So in the machining process, generally the deformation zone are the critical region where the material undergoes significant plastic deformation. We uh, can broadly categorize into three main areas like the primary deformation zone, the secondary deformation zone, and the tertiary deformation zone. Now, this primary deformation zone it locates ahead of the cutting tool, where the workpiece material first makes contact and undergoes severe compression and shear. The secondary deformation zone occurs along the tool chip interface, where friction between the chip and the tool face induces additional shearing and temperature. Additionally, the temperature rises. The third one, the tertiary deformation zone, is found along the workpiece and tool interface, where the tool faces generate heat, frictional heat, and further deforms the workpiece surface. Now, uh, understanding this zone, the understanding of machining or the mechanics of heat generation in this zone is very crucial for optimizing the cutting condition to optimize tool design and improving the overall machining efficiency. Coming to the next thermal aspect of machining, the machining temperature has various adverse effects which affect majorly the workpiece microstructure, then surface roughness, then tool life. Now, the workpiece microstructure is often affected by high temperature in the machining zone that may introduce several microstructural defects. Again, temperature or the heat generation in the machining zone can significantly impact the surface roughness, the tool life in the machining process. High temperature can lead to thermal expansion of the both tool and workpiece, which will result in dimensional inaccuracy and also increase surface roughness. Or moreover, the high temperature accelerate the tool wear by high adhesion process and high diffusion process, thereby reducing the hardness of the cutting tool and leading to a shorter tool life. That means our tool life will be very less. Now, through we can mitigate this effect through effective cooling and appropriate material selection, ensuring better surface roughness and enhanced tool life. Now, to mitigate the thermal aspect, there are two major ways by through which we can uh, not remove, but we can reduce the effect. It is not possible to remove all the thermal aspect 100%, but still we can mitigate or we can reduce it by great extent. Now the first way is the application of harder tool like the diamond cutting tool, for example, the polycrystalline diamond, PCT cutting tool, etc. Second process is the application of the cutting fluid. So among these two approach, the application of harder tool will result in the increased cost of the tool, which may not be feasible in every industry. So we'll be focusing more into the second approach, application of cutting fluid. So in this course or in this lecture, we'll be focused into the method where application of cutting fluid is done, because it is a comparatively cheap process and it can be followed in every industry. What is the difference? What is the importance of cutting fluid? Cutting fluid can lubricate. Cutting fluid can be used to lubricate between the contact surface. It can be used to cool down the cutting zone. It is used for chip evacuation, for surface finish improvement. Then it can be used for corrosion protection. It may used for tool life enhancement. It may give us tool temperature stabilization. The use of cutting fluid can help us to prevent rust in the workpiece, and it will help us in lower energy consumption. So coming to the importance or effect one by one. First is the lubrication between contact surface. Now, whenever we are using cutting fluid in the machining process, it can use as a coolant, which will uh, it will act as a lubricant between the tool and the workpiece, therefore reducing the friction and the wear. The lubrication minimizes the amount of heat generated from the friction, enhancing the efficiency of the cutting process and preventing damage to the both tool and workpiece. Second one is the cooling the cutting zone. That means one of the primary function of the coolant in machining is to dissipate the heat generated at the cutting zone. Because the coolant cutting fluid or the coolant or the lubricant, they are having different thermal conductivity than the different means a higher thermal conductivity than the base uh, tool or the workpiece. So by absorbing and carrying away the heat, the coolant helps to maintain an optimal temperature, which is very crucial for maintaining the integrity of the tool life and the workpiece. Third is the chip evacuation. Coolant helps in the effective removal of chip in the cutting area. Because coolants are used in high pressure, it can flush away the various debris or the chip, small chip, preventing them to for interfering with the cutting process, which can lead to smoother operation and reduce the risk of tool breakage. Next is a surface finish improvement. Using coolant can significantly enhance the surface finish because it helps to reduce the friction and the thermal effect then that can cause imperfection on the surface, which will lead to a higher surface finish, or in the other term it will help in lower surface roughness and more precise finish. Now the coolant often contain additive that protect the both tool and the workpiece from corrosion. This additive form a protective barrier on the metal surface, preventing oxidation and other corrosive reaction that could degrade the material over time. Next, coming to the next, by reducing the heat and friction, the coolant it can extend the life of the cutting tool. It can improve the tool life by lowering the operating temperature and reduce wear. Means that the tool will stay sharper for long time and it will require less frequent replacement, thereby improving the overall productivity and the cost efficiency. Next, the tool temperature stabilization. Now, the coolant or lubricant they help stabilization the temperature of the cutting tool. Consistent temperature control it prevents the thermal expansion and the contraction, which can lead into inaccurate and inconsistent in the machining. This stabilization is the key to maintain a precision in the throughout the machining process. Now is the rust prevention. Also, coolant can also serve as a rust inhibitor. They can create a protective film, like we have already covered in the corrosion prevention. Ne- Next, the lower energy consumption. Now, by improving the efficiency of machining process, the coolant or lubricant, it can contribute to a lower energy consumption, reduced friction, and better heat management. That means the less power is required to perform the same amount of work, which will lead the energy savings and lower operational cost. Coming to the various problem of cutting fluid, although we have discussed the advantages of using the cutting fluid like lowering operation cost, less heat generation, but there are often various problems in the cutting fluid. First one is the environmental impact, health hazard, then environmental sustainability, the issue of maintenance and disposable cost, the again fire and safety risk, then machining limitation. We can easily see that environmental impact is a very significant concern in today's scenario, because many coolant that contains chemical which can harm the ecosystem if it is not properly handled. The runoff, that means the waste from the machining operation, can introduce pollutant into the water source, affecting the aquatic life and potentially contaminating drinking and water supplies. Because nowadays, although maximum the industry they follow the guidelines, there may be some industry which may not implement all 100% sustainable process. So there is a very environmental risk in the system. So also health, next is the health hazard, which arises from the exposure from the coolant chemical, which can include carcinogen, that means uh, chemical which can cause cancer, or it may become irritant. The machine operator or other worker may experience a respiratory issue, skin irritation, or long-term health problem due to the prolonged exposure to the coolant mist and the residue. Now, coming to the environment stability, it is a compromise between the coolant formulation, which solely rely on the non-renewable sources or have a high carbon footprint. Additionally, the disposal of the used coolant can be challenging because it often requires specialist treatment process to neutralize the harmful components before being released into the environment. Maintenance and disposal cost be substantial compared to the environmental effect because the coolant system require a regular monitoring. It requires regular filtration and replacement to maintain the effectiveness and minimizing the environment impact. So disposing of the used coolant safely, it is it requires a significant expense or significant cost, particularly if it is required hazardous coolant. Also, the next one, the fire and safety, it risk are heightened bigger in the machining process because the coolant is a mixture of metal additive and a inflammable fluid which can create a combustible environment. So improper handling of the maintenance of coolant system, it increase the risk of fire, or it increase the risk of explosion, which poses a danger to the both personnel and the machinery equipments. Also, the machining limitation may occur or may arise due to the use of coolant, as certain materials or process may not be incompatible with the coolant application. For example, some high-speed machining operation may generate excessive heat that cannot be adequately dissipated with the coolant, which may lead to the machining defect or a tool wear. Additionally, coolant may interfere with the subsequent process such welding, painting, which will require extra step to remove the residue from coolant and thereby ensure the product quality. Now, further going into the cuttings of cut, problems of the cutting fluid, we are having one issue of chemical toxicity. The cutting fluid, the main function or the primary work of the cutting fluid is to lubricate the tool and workpiece interface, then thereby reducing the friction between the contact surface. Now, whenever we are applying cutting fluid in this very hot temperature, what will happen? The coolant will evaporate into mist. or it will generate smoke. So machining a smoke or emission during the machining, it will create a health hazard to the operator, because uh, in some environment it may not be possible to wear mask all the time, although it can be mitigated or reduced by using the various uh, factor like using mask or using different curtains like that we can, or using emission fan we can mitigate, but it is not possible to remove 100%. So now the International Agency for Research on Cancer, what they have concluded, they found that there are sufficient evidence that the particulates of mineral oil used during the machining are carcinogenic, that it can create cancer of the operator. So the table gives various chemical in the cutting fluid and the diseases. Like chlorinated paraffin, it can introduce folliculitis or dermatitis. Then polycyclic and nitrosamines, it can causes cancer. Nitrates in the cutting fluid, it can cause skin cancer. Endotoxin can cause respiratory irritation, asthma. Sulfur, lead, boron, zinc, etc. Uh, can causes pneumonitis or hypersensitivity. Or if the cutting fluid contains cobalt, then it can have bronchitis on the operator. Now, also this metal particle of the cutting fluid, they entered into the machining, and uh, if it stay on the machine for a long period of time, it may cause bacterial fungal population over the fluid. So it is a very essential to uh, mitigate these problems or reduce this problem. Also, we are having the physical hazard. Apart from the other hazard, we are having the physical hazard like disposing the cutting fluid. After the use, uh, we need to dispose the used cutting fluid in. Now, this disposition poses a substantial risk of the water and soil pollution. The chemicals used in the fluid that can lead to water sources, which will contaminate the aquatic ecosystem, or it may seep into the soil, which will affect the fertility and composition of the soil. Also, this pollution can have far-reaching consequences like both terrestrial and aquatic life, which will disturb the ecological balance and endanger biodiversity. So, we should have one alternative cooling strategy, which will be help to mitigate the various problems associated with the cutting fluid. Now, we can use various eco-friendly cutting fluid like sunflower oil, coconut oil, whereas like nowadays we are using various mineral oil like and canola oil we can use. Now we can use cryogenic machining. So cryogenic machining is done under extremely low temperature, like which is below negative 150 degrees Celsius, or in Kelvin scale it is 123 Kelvin. So the process generally uses liquid nitrogen. Next process is the MQL. MQL is minimum quantity lubricant. So to avoid or minimize the health hazard or the environment hazard, what we can do, we'll be using the cutting fluid, but we'll use the cutting fluid in a very minimum quantity. So it is also known as sometimes MQCF, also minimum quantity cutting fluid. So MQL, which it is referred to the use of precision dispenser to supply a very small amount of cutting fluid to the tool workpiece interface, which is typically at a flow rate of 50 to 500 milliliter per hour. So compared to the traditional flat cooling, in traditional flat cooling, uh, we are using almost 500 to 600 per minute. So we are using a lot of cutting fluid in the MKL process. So in one of the study, it was found that the cutting fluid cost almost 17% of the total machining cost. Thereby reducing the cutting fluid, the MQL can have enormously reduced the machining cost while saving the environment and the people. That means we can find a balance in the use of cutting fluid, use of the machining cost, while reducing the environment and the people. MQL, the minimum quantity lubricant, is also known as near dry machining because in dry machining we are not using any kind of cutting fluid. In flat cooling, we're using almost 500 to 600 milliliter per minute in flat cooling. But to balance in between this dry cooling and flat cooling, the MQL it requires the cutting fluid at almost 1 or 2 milliliter per minute. So it is also known as green machining because the sustainable nature of the cooling process. Now coming to the another alternative in machining, we can have one the help of the new advanced technology like nanotechnology we can incorporate in the machining process. Uh, Nanotechnology is the branch which comprises of the synthesis, engineering, and the utilization of material whose size ranges from 1 to 100 nanometer that are commonly known as nanomaterials. Now, based on the composition, the nanoparticles are generally placed into three classes: organic, carbon-based, and inorganic. The inorganic nanoparticles can have the nanoparticles that are made from protein, carbohydrate, lipid, polymer, or any other organic compound. The carbon-based nanoparticle that have the nanoparticle that's made solely from the or made 100% from the carbon atom. Famous example in this class are fullerenes, carbon black nanoparticles, carbon quantum dots, etc. So in this carbon-based nanoparticle, we can have different geometry like single wall nanoparticle, multi wall nanoparticle, etc. Now coming to third class of the nanoparticle, the inorganic nanoparticle. So this class comprises the nanoparticle which are not made of carbon or organic materials like metal, ceramic, or semiconductor nanoparticles. Next issue is the thermal conductivity of the nanoparticle. See, energy conduction from photon or known as lattice vibration or electrons as well as the accompanying scattering effect are the main sources of heat transfer in the nanoparticle. In nanoparticle, the thermal conductivity, the thermoelectric power, the heat capacity, and the thermal stability are the main element which includes the material thermal characteristics. The electrical and thermal conductivity of the nanoparticles are directly impacted by their size. The ratio of the particle surface area to the volume it increases hyperbolically as the nanoparticle size lowers. Now term the term nanofluid it was coined by Choi in 1995 in his paper presented in the 1995 at the American Society of Mechanical Engineers in winter annual meeting. So the term nanofluid refers to a base fluid or base liquid which contains a dispersion micronic solid particle that is nanoparticle with a typical length under 1 to 50 nanometer. Now this nanofluid has highly enhanced thermophysical property like including the thermal diffusibility, viscosity, heat transfer coefficient and thermal conductivity. Now the base fluid we can use like vegetable oil which are eco-friendly like vegetable oil, coconut oil, soybean oil, jatropha oil, paraffin oil, and we can use water also. So, except the base fluid, the nanoparticle that has been used traditionally by various researchers to produce the nanofluid are metal oxide like aluminum dioxide, copper oxide, then nitrate ceramics, then carbide ceramics like SiC, TiC, tungsten carbide, etc., or metals like silver, copper, iron, etc., or semiconductor like titanium dioxide, or also various carbon nanotubes like single walled carbon nanotubes, double walled carbon nanotube, multi walled carbon nanotube, and composite material also, which is like a nanoparticle core polymer shell composite. Now, to implement this nanofluid in the MQL, it is sometimes it is known as NMQL, nanofluid enhanced minimum quality lubrication. So NMQL is an efficient and clean and precision lubrication method, which is aimed to overcoming the bottleneck of the transfer technology in the MQL application. The nanofluid MQL machining has great potential in new sustainable industrial cutting technology. Now, one of the major issue is to how to produce the nanofluid. See, nanofluids are prepared by dispersing nanoparticles into a base fluid. So, as we have covered, already, base fluid can be any vegetable oil, like that, or nanoparticles may be metal oxide, organic, or different various carbon, and etc. Now, to prepare the nanofluid, the good dispersion is a very much prerequisite for the application of nanofluid. So, therefore, the various surfactants are used to enhance the quality of the or enhance the stability of the nanofluid. Also, beside the surface modulation of the dispersed particle and the application of strong force on the clusters of the dispersed nanomaterial may increase the stability of the nanofluid. So fundamentally, there are two methods to prepare the nanofluid, which are one-step method and two-step method. Coming to the one-step method, by the name suggests, it is a single-step method, which will in this method, the nanofluid preparation, it is a straightforward approach to creating the nanofluid, which are the suspense of nanoparticle in a base fluid. So in this method, traditionally, the nanoparticles are directly dispersed into a base fluid into a single step without the need of any additional processing or treatment. So that process typically involves mixing the nanoparticles and the base fluid using techniques like stirring, sonication, or agitation to achieve uniform dispersion. So in this method, some processes are avoided like drying, storage, transportation, and dispersion of the nanoparticle. By the one-step method, we can have a stable nanofluid by using the process like PVD, physical vapor deposition technique, in which the direct evaporation and condensation of the nanoparticle are carried into base fluid. But the main drawback of this method is the residual surfactant. But one of the key advantages in the one-step method is the simplicity and efficiency because it eliminates the need of complex procedure or multiple steps. This one-step process is a more cost-effective and time-saving process compared to the other method of nanofluid preparation. Additionally, the one-step method allows for precision control over the nanoparticle concentration and distribution within the nanofluid, which will lead to consistent and reproducible result. However, despite of the simplicity, the one-step method requires some careful optimization of the parameter, such as mixing time, temperature, the nanoparticle concentration to achieve desired particles such as stability, enhanced thermal conductivity. Also, the choice of base fluid and the nanoparticle is very crucial to ensure the compatibility and the desired performance characteristics in the resulting nanofluid. So overall, the one-step method offers a convenient, effective approach to prepare the nanofluid for various applications in the fields such as thermal management, energy, biomedicine, aerospace, etc. Next is the two-step method. Now, compared to the one-step method, it is the most economic method for large-scale preparation for nanofluid. Typically, in the two-step process, the nanoparticles are in powder form are introduced into base fluid in a predetermined amount. This production process in a very inexpensive and massive. But the main drawback is the aggregation of the nanoparticle. That means agglomeration of the nanoparticle into the bottom of the nanofluid. Now, to overcome this instability or to overcome the issue of the agglomeration, various surfactants is used in a low quantity. So, also the two-step method is a commercial method to prepare the nanofluid. Also, the various researchers prefer this method for production of the nanofluid. So, this is the flow diagram to produce the nanofluid. So in the first step, what happens in the first step is nanoparticles are synthesized or acquired separately. So this may involve the chemical synthesis, the physical vapor deposition, or other technique depending the requirement of the specific nanoparticle. So the resulting nanoparticle typically possess certain properties and may have coated with surfactants or functionalness to enhance the stability and compatibility of the base fluid. Now, these nanoparticles are weighted into a certain weight according to the requirement of the nanofluid. Into the also base fluid is calculated how much is required. Then both are mixed using by the direct mixing. So we can have different mm, method. Also after direct mixing, some quantities, very small quantity surfactants are used in this process. Next, the direct mix will go to for magnetic stirring and sonation or a various chemical treatment for a long time. So main goal to achieve a uniform dispersion of nanoparticle within the fluid, the it is required to have optimal thermal and rheological properties. So we need careful control of the parameters like temperature, pH, and mixing intensity, which is very essential to produce nanofluid with a consistent and desirable characteristics. So in summary, in this lecture we have given the introduction to the manufacturing process and the machining process. What are the various uh, machining process, then thermal aspect of machining process, then importance of cutting fluid in machining. So what are the various problems with the machining fluid or cutting fluid, then what is the alternative cooling strategy, then what is the use of nanotechnology in machining, the nanofluid in MQL, and the methods to prepare nanofluid. So these are the various references I have used for the slide. And in the next PPT, we'll be covering various topics like evaluation of nanofluid stability, how we evaluate the nanofluid stability, then how to evaluate the nanofluid thermal conductivity, then impact of various factor on the thermal conductivity, then impact of nanofluid on the machining process parameter. Then we need to analyze the toxicity, or we need to analyze the problems associated with the nanofluid assisted machining, and what are the environmental impacts of nanoparticles. So this thing we'll cover in the second lecture. So if you have any feedback, you can scan the QR code, or you can go to the Google form, Office form given in the slide. So if you have any query or any question, we'll cover in the next slide. So thank you so much.